Capturing raw physical reality, like the force of a high-velocity piston, and converting it into a calibrated electrical signal is the central challenge of instrumentation. Transduction is the active exploitation of fundamental physics to capture movement, force, and pressure. But measuring a slow, static change requires a physical architecture that is entirely different from one designed to capture high-frequency impacts. For precise geometric measurement, engineers rely on the linear variable differential transformer, or LVDT. For hyper-fast, solid-state measurement, the standard is the piezoelectric transducer. One device utilizes magnetic fields and internal geometry, while the other utilizes molecular distortion within the material itself. Selecting the correct sensor depends on understanding the foundational physics driving each device. We will deconstruct their internal architectures, trace their working principles, and identify their physical limitations. Relying on the wrong physical mechanism for a specific measurement regime leads to a complete failure of the data. The LVDT is an inductive, passive transducer that uses geometric positioning to measure linear displacement. This construction includes a primary winding, marked P, and a movable soft iron core that slides within a hollow former. When an AC voltage is applied to that primary winding, it generates an alternating magnetic field in the air gap. The high permeability iron core channels this magnetic flux, acting as a bridge to the surrounding coils. Two secondary coils, S1 and S2, sit on either side of the primary. They contain an equal number of turns to ensure symmetry. The electrical schematic reveals the specific wiring logic that allows the LVDT to function. S1 and S2 are connected in series opposition, meaning the induced voltages in each coil work against one another. This results in a total output voltage, the exact difference between the two secondary EMFs. At the null position, the core is perfectly centered. The flux linking with both secondaries is equal, and the resulting output voltage is 0. Moving the core upward increases the magnetic coupling with S1. This induces a higher voltage in the first secondary, creating a positive output. Moving the core downward shifts the coupling toward S2. The output becomes negative, signaling a 180-degree phase shift relative to the primary. This makes the L geometry. This V-shaped curve represents the LVDT's output signal as the core moves through its range of travel. The central intersection on this graph represents the absolute null point, where displacement is 0. Engineers use the phase of the signal to determine which side of that null point the core is on. Because the core floats inside a hollow bore, the LVDT operates with no physical contact between the moving core and the coils. This frictionless design provides the LVDT with infinite theoretical resolution and a significantly extended operating life. It is effective across ranges from fractions of a millimeter up to 250 millimeters. However, the reliance on magnetic flux makes the sensor vulnerable to external magnetic fields. Proper operation requires heavy stainless steel shielding to prevent signal corruption. These characteristics make it ideal for static measurements, or for use as a secondary transducer attached to a Borden tube for pressure sensing. Ultimately, the LVDT trades a larger physical footprint for durability and static spatial precision. In the solid-state realm of the piezoelectric transducer, the mechanics of measurement are entirely internal and operate significantly faster. Piezoelectric materials, like quartz or PZT, are active sensors. They produce an electrical charge through the imposition of mechanical stress without requiring an external power source. A typical piezoelectric load cell consists of a PZT disc sandwiched between two metal electrodes. In its resting state, the crystalline domains inside the material are randomly oriented, resulting in a neutral electrical state. When a mechanical force is applied across the face of the crystal, it compresses the lattice. This stress distorts the crystal lattice, shifting the internal dipoles and forcing positive and negative charges to accumulate on opposite faces. This distortion generates a voltage across the electrodes that is directly proportional to the applied force. That voltage is a function of the material's thickness, the applied stress, and the specific piezoelectric constant of the crystal. There are no moving cores here. The solid material itself acts as the transduction mechanism. These sensors convert kinetic energy directly into electrical potential through molecular deformation. The solid-state design introduces a specific constraint. If a constant, heavy weight is applied to a piezoelectric sensor, the reading will not remain stable. The initial compression generates a sharp voltage spike, indicating the impact of the force. However, under a sustained static load, the generated electrical charge leaks away through the crystal and the circuit, causing the output to decay to zero. Consequently, piezoelectric sensors are incapable of measuring static conditions. If the applied force doesn't change, the sensor cannot maintain a signal. Additionally, the ceramic materials used are brittle, and their resistivity is highly dependent on ambient temperature. Despite these constraints, the lack of moving parts allows for a high-frequency response, making them ideal for capturing transients that last only microseconds. This makes them standard for microaccelerometers, ballistic impacts, and ultrasonic transducers. Piezoelectric sensors trade static visibility for the ability to monitor the most rapid physical events in engineering. Choosing between these paradigms is a matter of matching physical capabilities to the specific measurement environment. The LVDT provides a passive, geometric solution utilizing magnetic flux for long-term static displacement measurement. The piezoelectric transducer provides an active, material-based solution for zero-power, high-frequency dynamic force measurement. An LVDT used for high-impact shocks will fail mechanically, while a piezoelectric sensor used for static weight will fail electrically. Meaningful data analysis depends on a deep physical intuition of exactly how the signal was born within the sensor.